Let's discuss an important topic in linear algebra: eigenvalues and eigenvector. Eigenvalues and eigenvectors. Okay, so first let's start with the basic equation. What does an let's first understand what does an eigenvalue means and what does an eigenvector mean, because this topic is quite important in various branches of engineering. Maybe it's mechanical engineering, or it has various applications in, like for example, in mechanical engineering, if you have a stress tensor, then the eigenvalues of the stress tensor means just like a stress matrix, and the eigenvalues basically represents the eigenvalues. Basically, if you happen to find out the eigenvalues of that stress matrix, which is 3 by 3 at a point, then those three eigenvalues represents basically the principal stress or the maximum normal stress at that point. So it has physical significance in various branches as well. So I gave an example: if the matrix happens to be an stress tensor, then the eigenvalues represent the principal stresses: maximum, intermediate, and the minimum. So you have three principal stresses, and therefore the three eigenvalues represents those, and the eigenvector represents the principal plane. So this is from the application point of view, but first let's understand how to find what is the meaning of eigenvalue, and then uh, how do we find out eigenvalues, and then what do we mean by eigenvectors in a mathematical. So let's do a complete rigorous mathematical treatment. So if I take A to be a square matrix, and say if I have a vector x, so this is a matrix and this is a vector. So if this vector operates on this matrix such that the result is I get some multiple of the same, that is, if I multiply a square matrix with a vector, and if x happens to be in such a way that if I get the after multiplication some constant, so this is just a constant times the same vector. So it can happen, I mean, for every matrix A, there can be a vector x. When you multiply that matrix with a vector x, you may get some multiples of the vector. Okay, so the starting equation is this. Now if I just do a mathematical treatment of this, bring lambda this way, okay, which I can very well write in this way, and this I can again write this as lambda. Well, x can be written as ix, where I is basically identity matrix and x is, so it's like ix identity matrix. If you can, identity matrix we all know it is 1 0 0 0 1 0 0 0 1. Okay, so this matrix, when you multiply with any vector, you will get the vector, right? You will get the same vector. So I am just writing in that way. Now I can take, so by just the properties of multiplying, I can take a minus lambda I to be common, right, to 0. Okay, so this basically is a system of linear homogeneous simultaneous equations. So what we have learned in the solution of equations, so if you recall, this is basically a system of linear set of simultaneous linear equations which are homogeneous. Why homogeneous? Because the right hand side is 0, that's why it's homogeneous. Okay, so now for we know that for a non-trivial solution, so we know that for non-trivial, now trivial here means, the trivial solution here means x1 h2 till xn is 0. For non-trivial solution, that is x1 not equal to 0, h2 not equal to 0, something like that. Okay, because for trivial, now trivial, let me just define what is trivial here. So trivial will be h1, h2, h3, so on till hn is 0. Okay, but we are not looking for that. So we have already seen that when you have a homogeneous linear set of linear equations, for a non-trivial solution, your det of this a minus lambda I has to be 0. Okay, that is for x eigenvector. I mean, remember, okay, let's be cautious here. I have not defined anything. So let for any vector x to be a non-zero vector, that is its elements to be non-zero here, then I mean, when you solve this, say you can take A to be a 3 by 3 matrix. So this becomes basically three equations, simultaneous equations, and in three variables. And now when you solve this, the default is the trivial solution where x1, h2, h3 is 0. But what I'm saying is, for a non-trivial solution to happen, the rank has to be 2, right? Rank of that has to be 2, and the rank of both augmented matrix and the A matrix has to be 2. And rank has to be 2 means obviously the third order determinant should vary. I mean, the largest determinant should vanish, and that's what we have done here. The determinant is 0 for it to have a non-trivial solution. That is quite obvious from the solution of simultaneous equations which we have seen for homogeneous case. So now determinant has to be 0. So how do I find out that? Now say if A happens to be a matrix something like this: A1, A12, A13, A21, A22, A23, and then A31, A32, A33 is, say, A matrix, and therefore A is A matrix, and therefore A minus lambda I would be A11 minus lambda, right? Or okay, A12, because I is something like this. Lambda I would be something like this: lambda 0 0, basically multiplying identity matrix with some constant. Okay, and now if you subtract A minus lambda I, it will be something like this. So all the lambdas will be subtracted with the diagonal term. Sorry, there is no lambda here, only with the diagonal term. This will be there. Now det of this, if you set 0, okay, then basically you get a cubic equation in lambda. Okay, so now in the mathematics literature, this is called the characteristic equation, and the roots are called the eigen values. So this is just from the mathematical point of view. Application, as I told you, from the mechanical point of view I told you. So the roots are basically the eigenvalues. Okay, and this is basically called the characteristic equation, and the eigenvalues of matrix A, because everything what we are doing is on the matrix A. So of matrix A, so eigenvalues of matrix A. So that is the thing. And now when you just substitute back in this equation, when you substitute back everything, once you have found out lambda, substitute back in this equation, you can end up finding x. So that x corresponding to value of lambda which satisfies characteristic equation So that X is called the eigen vector. So this is just the definition of matrix. Okay, so this is just the definition of so we have seen how to find out eigenvalues, how to find out eigenvectors, and what is characteristic equation, that is nothing but that of A minus lambda I. So now let's just so here one important thing is that for every value of lambda, like say if A happens to be a square matrix, so the point to be noted here is that for every value of lambda, that is for every value of for every eigenvalue there, okay, so when you solve for X, it gives the eigenvectors. So for every value of lambda you will get one eigenvector. That's what is the point. Okay, and there are a couple of points to be noted here, so let me just write down those. First point, the set of eigen values is called spectrum of A. So just if you have found out say A is a 3 by 3 matrix, so you will get the cubic equation for 3 by 3, and then that set would be is called spectrum, and the largest value out of the absolute values of eigenvalue is called spectral radius. Okay, so let me just write down largest. So these are just purely definitional. Largest of the absolute value of the eigen values is called spectral radius of A. Okay, and multiplying the eigenvector by a scalar or multiplying the matrix A gives the same result. So that's the point. And for a given eigenvalue there can be different eigenvectors, but so this is an important point. So for a given eigenvalue there can be different eigenvectors. This actually, when we solve one example, this point will be clear. So next we will be solving one example problem. But for same eigenvector there can't be different eigenvalues. What it means is that for a given eigenvalues there can be different eigenvectors, which we'll see, because the equation, the set of simultaneous equations has infinite solution, as you all know, for non-trivial case. So then you have lot of options. For a given value of eigenvalue you can have different eigenvectors, but then the reverse is not true. So for the same eigenvector there can't be different eigenvalues. So we'll see all this, but let's first take an example. Okay, so this is just the definition here. Let's take an example at this point just to find out the eigenvalues and eigenvectors, and just whatever the basic concepts which we have introduced, let's be clear with that. Okay, so let's solve one problem here. Find the eigenvalue and the eigenvector of matrix which is given something like this. Okay, so you have a matrix for which we need to find out eigenvalue and eigenvector. Okay, so let's solve it. This is quite a simple problem, but whatever we have defined, let's understand it. So first thing is, in order to find out eigenvalues, the main equation is the characteristic equation which we have seen. It comes from Ax is equal to lambda x. So the characteristic equation of matrix A, basically the roots of that will give you the eigenvalues. So the characteristic equation is what? Mod A minus lambda, this is det A minus lambda I. So det A minus lambda I would be det of, we have seen the diagonal terms, you have to just multiply, you have to subtract lambda and then take the det. It's as simple as that. Now determinant, because it's a 2 by 2 matrix, so the determinant of this would be just AD minus BC. If you have something like this, A, B, C, D, okay, now the det of this would be just the cross multiplication, so AD minus BC for a 2D matrix. And for 3D you know how to find out, so which we have seen already. So now it will be 5 minus lambda into 2 minus lambda minus 1 into 4, 1 into this is just 4. Okay, so this is the det. So det comes out to be, if you just simplify this, 5 to 10 minus 5 lambda minus 2 lambda plus lambda square minus 4. So this value comes out to be lambda square minus 7 lambda plus 6 is equal to 0. Okay, and that's what you have to set. You have to set the characteristic equation to 0. This is the characteristic equation. So now the roots of this equation, would be this. You can just simply factorize. So lambda square minus 6 lambda minus 6 plus 6 is equal to 0. Okay, so this, the roots basically are the, let's factorize 1 comma 6. So the eigenvalues is 1 and 6. So these are the eigenvalues. Now corresponding to this, let's find out the eigenvector. So for the eigenvector, you have to again start from that A minus lambda I into x is equal to this equation. Okay, and from this, because from definition x is an eigenvector when you substitute the values of lambda in this. So now this becomes, if you just simplify, this becomes 5 minus lambda 4 1 2 minus lambda and x, let the elements of x be x1 and x2. Okay, 0. Okay, so this is the general equation. Now for lambda is equal to 1, okay, let's substitute it. For lambda is equal to 1, what will I get when I substitute this? I'll get 4 4 1 1 x1 x2 is equal to 0. So this is just a set of simultaneous equations which I can just expand it and write in this form. 4x1 plus 4x2 is equal to 0. X1 plus x2 is equal to 0. So basically these two, if you just divide the first equation with 4, it represents same equation. So let h2 be k, and therefore the x1 will be minus k. So the eigenvectors are minus k and k. Okay, this is just a simple way to mention. Now most of the time what we do is we end up, so k is just a constant, so we end up, now k, because you know that the set of simultaneous equations for a homogeneous case, the non-trivial case, solutions are infinite. So that's why now for this lambda 1, the eigenvector is basically minus k and k. Okay, and k can take now values ranging, k is basically an integer, all the real numbers, it can take any values. In this equation, k is basically an integer, it can take any, k is not an integer, it's basically a real number, it can take any values. So what we do is we mention that for lambda is equal to 1, the eigenvector is minus k comma k, and sometimes we give values to k, like if k is say 1, so all this are your eigenvectors, minus 1 1. Okay, you can say 1 minus 1 also. I mean, I can take x1 as k and x2 as minus k, so it doesn't matter. And instead of 1 comma 1, I can take 2 minus 2. I mean, I can take k as say minus 2. So all these are all eigenvectors. So in standard we represent by this way. Okay. So that's why for a given value of eigenvalue there can be many eigenvectors. Okay. Now we had another case where lambda was 6. For this case, let's find out the eigenvector or eigenvalue. Okay, so eigenvector we already got. This is the eigenvalue, lambda is equal to 6. Now substituting in that expression, that is 5 minus lambda 4 1 2 minus lambda into x1 x2 is equal to 0. Is equal to 0 you can write. So now if you substitute lambda is equal to 6, you will get minus 1 4 1 minus 4 and x1 x2 is equal to 0. So if you expand this equation, you can get two equations. So let's see, minus x1 plus 4 x2 is equal to 0, x1 minus 4 x2 is equal to 0. So basically they are not independent, and this can be, if you multiply first equation with minus, you can get the second equation, right? So the general equation is basically x1 minus 4 x2 0. So what we do is we take h2 as k, so x1 will be 4k. Therefore the eigenvectors would be 4k and k. So this is the standard form of the eigenvector for lambda is equal to 6. So normally if you can put k1, then 4 1 is eigenvector. If you take k2, then 8 comma 2 is eigen. So all those are eigenvectors. So one point is clear, that for a given value of lambda you have lot of eigenvectors. You can have different eigenvectors. Okay, but the back is not true. That is, for given eigenvector there can be only one eigenvalue. You can't have multiple eigenvalues for a given eigenvector. Okay, because this form is fixed for a given eigenvalue. So now, when you mention, so sometimes like they may ask you, like, check whether this is an eigenvector or not. Check given an eigenvector whether this is an eigenvector of the matrix or not. So you have to just multiply that eigenvector with the matrix and check whether you are getting the constant multiple of that. That's the thing. Just use the basic definition. Okay, let's now see the properties of eigenvalues. Okay, so we'll see some important properties of eigenvalues, and then basically properties of eigenvectors, and then we'll solve some other problems of eigenvalues and eigenvectors. Okay, so properties of eigenvalue. The one important property, the first one being is the sum of the eigenvalues of a square matrix, or basically of a matrix, okay, is equal to sum of its basically diagonal elements, sum of its diagonal elements. So this comes from this basically comes from the characteristic equation. Like when you say, if you imagine a 3 by 3 matrix, okay, the cubic, I mean, when you will get a cubic characteristic equation for 3 by 3 matrix, and the sum of the roots, sum of the eigenvalues will be basically the sum of the diagonal elements. Okay, sum of the eigenvalues will be, so that this is a pretty standard result, and it basically boils down to finding out the sum of the roots for an eigenvalue, and that's it. Okay, so you can actually just derive it also, but I'm just stating down these important facts. And this, so that was about sum. Now the product of the eigenvalues of a matrix is basically equal to the determinant of that matrix is equal to its determinant. Okay, so these two are important properties. So basically lambda 1, lambda 2, lambda 3, if you take product, I mean if you take a 3 by 3 square matrix, then lambda 1, lambda 2, lambda 3 would be basically the determinant of material. So let's write down in these two in mathematical form. So lambda 1 plus lambda, say if I have for a square matrix, for a 3 by 3 matrix, the eigenvalues lambda would be sum of the diagonal elements, and the product for a 3 by 3 will be basically the determinant of A. Okay, so let's look at the other properties. Now the other property being, this is an important property, matrix A and A transpose has same eigenvalues. Okay, so let's try to derive this fact. So let's start something like this. From the characteristic equation you have something like this. Now we know that this is the determinant. Okay, so this I can write that of A minus lambda I. Now if you consider, okay, now we can write that A minus lambda I whole transpose is equal to that of A minus lambda I, because that of some matrix transpose is equal to the det. So if you have, say, det of some matrix, that value is equal to that of the transpose of that matrix. Now this I can write as that of transpose, I can just take inside, minus lambda I transpose. Okay, basically that of A plus B transpose is that of A transpose plus B transpose, something like that. Now I transpose is basically I only. Okay, A transpose is A transpose. I transpose identity matrix, if you take the transpose, it comes out to be identity matrix only. Okay, so ultimately we have shown that this is equal to this, and we all know that. So finally this is equal to this. What we get is that of A transpose minus lambda I is equal to that of A minus lambda I, which means the eigenvalues, because this that of A transpose minus lambda I will give you a characteristic equation, and that of A minus lambda I will give you a characteristic equation. But then one thing is, lambda is same here, so eigenvalues of A or A transpose, the roots will be same. Once you either do it on the left hand side or right hand side, the roots will be same because the characteristic equations are same. So eigenvalues are same since the characteristic equation is same. Equation is same. Okay, so that's the basic about the eigenvalues. Now let's see some other properties. So this property we have actually proved it also, but let's see some other properties. So if lambda is eigenvalue of a matrix an orthogonal matrix, okay, so orthogonal matrix means your A and A transpose is I, Okay, so if lambda is an refined matrix, then we have proved that 1 by lambda is also its eigen value. Okay, so this is an important fact. So let's see some other properties. So in general, one can write that if lambda is an eigenvalue of the matrix A, then A inverse has eigenvalue 1 by lambda. For AM has eigenvalue lambda power m. Then Ka has eigenvalue k times lambda, where k is scalar here, and A plus Ki has eigenvalue lambda plus k. So these are based on a lot of these you can easily derive it actually. Starting everything, the basic is starting with the characteristic equation. So this has eigenvalue lambda minus k whole square. So we have seen some important properties, and in general we have seen, like if lambda is an eigenvalue of the matrix A, then A inverse will have eigenvalue 1 by lambda, A power m will have lambda power m, Ka will have k lambda, A plus Ki will have lambda plus k. So in such, so important properties are your sum of the eigenvalues and the product of the eigenvalues, and noting that A and A transpose has same characteristic equation, so has same eigenvalues, and this important properties. So now let's see some properties for the eigenvectors. Till now we have seen the properties for the eigenvalues. So now let's see properties of eigenvector. Okay, so one thing you would have noticed in that example, that eigenvector is not unique. Eigenvector x of matrix A is not unique. So unit means for a given value of lambda, or for a given eigenvalue, I can have infinite eigenvectors, right? Because there is a constant k involved, because it basically comes inherently, this property comes from the solution of those homogeneous simultaneous equation, which was the starting point. So what I mean is that if so I can always say that if xi is the eigenvector, okay, then Cxi is also eigenvector, where C is some constant multiple, okay, some constant. So this property we have already seen in the example, okay. And also another property is that if lambda 1, lambda 2 and so on till lambda 1, which are the eigenvalues, are distinct, then you can say that x1, h2, xn are linearly independent. Now linearly independent means when I try to express some when I try to express, say x1, h2, h3, something like this, ah1 plus bh2 plus ch3 plus so on txn, is equal to 0, then it happens that A is equal to 0, B is equal to 0 and C is equal to 0, so on, I mean till whatever t is equal to 0. Okay, so this is a case of linearly independent. Okay, so that is one important properties for the eigenvectors. So if you can express sum of any linear combination of vectors to be 0, and such that those combination factors, the multiplying factors are also 0, then the vectors are called linearly independent. This we have seen earlier. Okay, and another important property is that two eigenvectors are called orthogonal vectors. Any two eigenvectors if you take for a matrix, okay, two eigenvectors are called orthogonal vectors if your x1 transpose x2 is equal to 0. So now if it satisfies this, then you call those vectors are orthogonal. Okay, so important point here you have to remember in eigenvectors is that it's not unique for a given value of eigenvalue. And now eigenvectors of a symmetric matrix basically corresponds to different eigenvalues which are orthogonal. Okay, so important properties of this which we have seen. Okay, and mostly I mean from gate point of view, it's just important to remember what is an eigenvalue and what is an eigenvector, because most of the time if you look at the previous gate questions which will anyhow solve it in this session, so always like given a matrix you should be able to find out what are its eigenvalues and what are its eigenvectors, and given an eigenvector you should be able to test whether this vector is an eigenvector of this matrix or not. That it should satisfy that equation. A capital X has to be lambda x. A capital X is equal to be lambda x. So the basic definitions are important. Important properties you need to just remember it, but then the derivations and all that you can always go through. We have seen one important derivation, that A and A transpose has same characteristic equation and thereby same eigenvalues, but all this Hermitian matrix, what happens to the eigenvalues of Hermitian matrix and all that, I don't think that is that important. But basic properties for eigenvalues, like sum of the eigenvalues is equal to sum of its diagonal elements, part of the eigenvalues of a matrix is basically equal to the determinant of the matrix. These two are important. And then A and A transpose, what happens, and if a matrix is orthogonal, that is A into A transpose is I, then how are the eigenvalues related? So just these 3 or 4 important properties and for eigenvalues. And for eigenvector you just need to remember that for a given value of for a given eigenvalue the eigenvectors are not unique. That's it. So let's now move to different so till now what we have seen is we have seen the definition and then we have seen the properties. We have solved one example, just an introductory example to know what is eigenvalue and what is eigenvector, and then we have seen the properties, basic properties of eigenvalues, important properties of eigenvalues and eigenvectors. So now let's move on to an important theorem called Cayley-Hamilton theorem. So we will not derive it, we will just state the thing and what it means in this eigenvalues stuff, what Cayley-Hamilton theorem means, and then we will try to solve some problems on Cayley-Hamilton theorem and the previous gate questions on this eigenvalues and eigenvectors. So this is an important topic in all the branches. Always you can expect a 1 mark or a 2 mark question on eigenvalues and eigenvectors.